Start broadcast. Welcome, ladies and gentlemen, to this second web seminar organized by SMARTEC. I am Luca Manetti.
The broadcast is now starting. All attendees can now hear you.
So welcome, ladies and gentlemen, to this second web seminar organized by SMARTEC. My name is Luca Manetti, and I will be the first presenter of today. We will present you two case studies, two projects. A first project concerning bridge monitoring in the United States, the I35 bridge in Minneapolis. And then the last case study will be presented by my colleague Dr. Branko Glisic, and it will speak about buildings monitoring in Singapore. So you should hear my voice through your PC speakers and headset. If you have questions, you can ask them by using the panel on the right of your screen, and we will be able to answer online using the question panel as a kind of chat, or at the end of each presentation we will dedicate a few minutes for answering other questions, or if you don't get any answer during the presentation, we will come back to you by email. Later on this week you will as well receive a link to this PowerPoint presentation in PDF as well, and you will be able to download the whole session and play it using a multimedia player. And then at the end of this presentation you will also be prompted for a few questions. We kindly ask you to answer these questions. They are very useful for us in order to improve the quality of such seminars. So as I said, we will present you two case studies, two projects. The first one is the I35 bridge in Minneapolis. And again, at the end of each presentation, we will dedicate a few minutes for your questions. So let's start. Let's start with the first presentation. If you hear me stopping for a while, I'm just waiting for the last of your screens to be refreshed, so I apologize. Here we are. So a short description of the project. The old I35 bridge in Minneapolis collapsed on August 1st, 2007, and several people were killed. So a new bridge was built at the same location. In fact, it's not a single bridge. The new one consists of two twin pre-stressed reinforced concrete bridges. Everything was done very quickly, about 13 months between the collapse of the old bridge and the opening of the new one. And this was one of the first, or is actually one of the first examples where in the, well, a structural health monitoring system was included from the very beginning of the planning phase of a bridge. So this slide is one of the first pictures taken from an helicopter showing the collapsed bridge in August 2007. Here we are. So you see on the right hand side the collapsed bridge. And few numbers about the old bridge. It was opened to the traffic in 1967, and it was scheduled for reconstruction between 2020 and 2025. And it's interesting to note that the first reports reporting damages, in this case cracking in the approach spans, is dated 1997. And from this time they repaired, obviously, and they kept monitoring the discovered damages. During this collapse of last year, 13 people died and 145 were injured. And Minnesota Department of Transportation calculated cost per day of approximately $400,000 per day due to non-availability of the bridge. And additionally, always the Minnesota Department of Transportation and the Department of Employment and Economic Development estimated the economic losses for Minnesota economy in approximately 17 million for year 2007 and 43 million in 2008. The next slide shows again few other pictures of the collapsed bridge, and on the top left side you see a picture of the old bridge. Here we go. So concerning the old bridge and the causes of the collapse, so the first exams seems to identify in fractures in the gusset plates the main cause of this collapse. So the design of the new bridge started immediately after the collapse event, and the new bridge foresees let's say 4 spans for a total length of approximately 370 meters. The longest span is the span number 2, the length of about 154 meters. The new bridge is designed for a 100-year lifespan, has 10 lanes of traffic. In fact, the 2 twin bridges has 5 lanes each. The bridge is approximately 51 meters wide, and it's ready to accommodate future light rail transportation on the external lanes. The next slide shows a few other pictures of the new bridge in the design phase. So as I said, the new bridge was opened to the traffic in September 2008. I don't exactly remember the day, maybe the 14th of September. And it was built in a record time of 339 days from the beginning of the project to the opening. I'm still waiting for this new slide to be updated on the last of your screens. That's why I'm waiting. So it is important to note that, as I already mentioned, this is one of the first examples where the instrumentation of the bridge was designed and defined since the very first design stage, and with the cooperation of many different actors. In particular, all the let's say entities involved in this construction project were also involved in the definition of the monitoring system to be installed in the bridge. So the designer, the contractor, the owner, the University of Minnesota as a research institute, and obviously the SMARTEC group and a few other companies delivering and installing the different sensors and systems worked in strong cooperation in order to design a system or systems fitting the true needs of such structural health monitoring instrumentation. And these needs were included in the bridge bidding proposal, in the bridge design, in the bridge executive plans, and also in the fast construction planning. So we are really talking about a smart bridge, and where the sensor monitoring system was really integrated into the bridge and covering 5 different areas. So the first area is the support during the construction processes. Second, the record of structural behavior, so the true monitoring of the structure basically. The control of the automated anti-icing system installed on the bridge. The control of the intelligent transportation system, and the bridge security. Many different kinds of sensors were installed in the bridge, starting from strain gauges for local strain monitoring, for local curvature and concrete shrinkage and creep monitoring. Thermistors for temperature monitoring, temperature gradients and thermal strains. Potentiometers on the joints for the joints movement monitoring. Accelerometers for the dynamic monitoring of traffic-induced vibrations and modal frequencies. The SenseCore corrosion sensors presented during the first web seminar for concrete resistivity and corrosion current monitoring. And of course, long-gauge fiber optic sensors for average strain distribution along the main spans, average curvature, deformity shape, and detection of cracks. And it's important to note that such sensors are optimized also for dynamic measurements. So currently static measurements are performed using a SOFO 6 reading unit, but it will be possible in the future to scan and read dynamically the same sensors using a SOFO dynamic unit. And these for dynamic strain, dynamic deformity shape, vertical mode shapes, and dynamic damping measurements. Few slides for showing you how the structural health monitoring system was integrated in this project from the very beginning. So all the plans and construction plans of the bridge already include a section showing exactly which sensor has to be installed where. Still, some of you do not have the screen refreshed. Let's wait for a few seconds more. Here is the first slide showing a side view and a top view of the bridge. And then the next slide shows a cross section. I can see from the slide exactly where, but you can see the density of information included in such plans concerning sensors position, junction boxes, ducts, cables, etc. So each component of the structural health monitoring system was placed and designed and formalized in plans. I will, with the next, waiting for the last of you to have the screen refreshed, I will introduce then the next 4 or 5 slides where the three-dimensional positions of each sensor will be. Okay. I jumped a few slides forward, so now I'm waiting to see what's going to happen on your screens. It seems that today the connection is not so performant as it should. Here is it. Okay, so yes, now you should have the structural health monitoring system plans slide number 2 showing the cross section. I was mentioning showing the position of each component of the monitoring system at this location. Okay, and here I jumped to the last slide showing the position of the sensors. We are talking about the SOFO sensors. So SOFO sensors are installed on span number 2, which is the longest one. We have 12 sensors installed along the span, 6 on each side, symmetrically, and couples of sensors are installed at the same location, one sensor on the floor and one sensor on the ceiling. We used, so as I said, SOFO sensors optimized for SOFO dynamic with active length of 4 meters. All the sensors are interconnected into a junction box installed exactly in the middle of the span. And then with a multi-fiber extension cable, all the signals are pulled to the SOFO B reading unit located at the end of the bridge. The SOFO B reading unit is integrated into the local LAN, since many other sensors and systems are interconnected into the same monitoring system, so everything is connected to the local LAN. That's why the SOFO B is equipped with a additional TCP/IP communication module. The next slides will show how the sensors are installed in the bridge. The first slide is showing two sensors installed on the bottom. Here is one. The sensors were protected because we installed the sensor in the very last phases of the let's say of the construction. So there were many activities running in parallel. So we needed, in order to protect the sensors during installation phase, we needed to protect the areas, avoiding people to step on the sensors. But right after installation, we protected, all the sensors were protected with such ducts. All the cables, all the passive parts of the sensors cables then are running along the span through ducts. Here you can see one, and here you can see the duct. You can also see that the environment inside the bridge was very dusty. The next slide shows where the control room is located, as I said, at the end of the bridge, a prefabricated container, a big one for all the infrastructure for the anti-icing system, and then on the left side of the next slide, it will appear on your screens, you can see the smaller container containing all the racks where all the electronic devices and reading units and servers are installed. Okay, so this is the small container with the control center. All the sensors okay, I answer a question that arrives. Only one bridge is equipped with the SOFO sensors. The southbound exterior span 2 is the only span equipped with the 12 SOFO sensors, while all the other, let's say, conventional sensors, vibrating wires, potentiometers, accelerometers, are distributed over all the girders of the twin bridges. All the data are merged into the SOFO SDB, and this slide shows a simulation of what the end user can see. So on the location where the sensors are installed, text boxes will show or are showing the real-time values of the measurements, and then according to the thresholds that are set for these sensors, different colors, meaning different behaviors. I will also show you few results during the first day, right after the installation and before the opening of the bridge. The upcoming slide will show 6 days of continuous hourly measurements of the SOFO sensors. Let's wait a few more seconds. Okay, you will see as soon as the slide appears on your screens, you will see the typical day-night cycles on the sensors due to the temperatures. It's obviously you have sensors that are more reactive to these temperature changes, other not, but all the sensors are showing the same trends. And this first screenshot will also highlight the day-night, well, the duration of the night cycle, which started approximately around 4 p.m. with the temperature decrease, and then the lowest temperatures in the breach were reached approximately at 8 a.m. And on the bottom right, you have a zoom of this behavior. Before the opening of the breach, obviously load tests were performed. This is a screenshot showing such tests where in different steps different loads were carried on the breach using big trucks. The tests occurred by night. So the slide first of all shows a trend downwards of the measurements, and that's why I mentioned it before, the day-night cycles, because in this case you see that all the measurements, all the sensors are showing a downtrend, but that's because the test was performed between 4 p.m. Well, this acquisition started at 4 p.m., the test started around 8 p.m. and then stopped at 5 p.m. in the morning. And then you see the different jumps corresponding to the different loads on the breach. And just note the scale, this is 0.1 millimeters. So concerning the load test, the next slide shows a side view of the breach. Here I have put all the 12 sensors, but we just focus on two couples, the 6A top and 6A bottom in proximity of this pier, pier number 2, and the 6I T and bottom approximately in the center of the span. So the load test, during the load test, different loads were applied on the breach, and the situation is obvious. The breach will react to this load with a kind of deflection in the mid-span. This means that according to what we expect to happen, the top sensor on the pier should get tension, while the bottom sensor should get compression. But on the other hand, in the center of the span, the top sensor should get compression and the bottom one should get tension. And in fact, zooming and focusing only on the two or on these four sensors, the measurements taken during the load test confirmed this expected behavior. And again, here we are talking about very small deformations, so this is much less than 0.1 millimeters. So I'm going to end the presentation of this first case study with a few acknowledgements. The Minnesota Department of Transportation, the Flatiron Manson Corporation, and of course the University of Minneapolis, which will be responsible for the management of the measurements and the analysis of the results. Okay, I think we can switch now the presenter. I will give the microphone to my colleague, Dr. Branko Glizic, for the next presentation. Maybe just before we switch, if you have more questions about this first case study, we will dedicate you can write them down and we will answer them online or at the end of the presentation. Thank you very much.
Okay, so my name is Branko Glišić, and I will continue with the presentation on the Punggol project in Singapore. So this project is actually a kind of pilot project that is performed on high-rise building monitoring. I will start with introduction, then I will continue with monitoring criteria, long-term measurements from year 2001 up to a few days ago. And then I will also show some other type of the measurements that we did, like 48-hour continuous measurements, then post-tremor evaluation that we did in 2005, and I hope we'll have a time to make some conclusions at the end. So the Punggol project actually started as collaborative study between HDB Singapore, which is practically public housing authority in this country, and SMARTEC in Switzerland, with the purpose to perform monitoring as a part of quality assurance and preventive maintenance, and in order to understand the structural behavior of those high-rise buildings. So it was decided to perform long-term lifespan structural monitoring, and we selected SOFO monitoring system for this. And nowadays we have more than 200 buildings that are equipped with the sensors in Singapore. And that's what I will present here is actually the status of more than 7 years long-term monitoring performed on very first building, which is called Punggol. And it will include monitoring during the construction, then 48-hour continuous monitoring sessions, and finally the post-tremor evaluation that is performed in year 2005. So let's start with monitoring criteria. It was decided to monitor critical structural members because the building is, high-rise building is very tall. There is a lot of elements that can be monitored, and it was decided to focus only on the critical structural members. And one of the reasons is obviously the cost that should be affordable. Then it was decided to perform monitoring on both local, column, and global building level. It was decided to perform long-term lifespan monitoring, including the construction stages, and to focus more to structural than to material monitoring. So at the end, in order to keep the costs affordable and low, but without affecting the performance of the monitoring system, it was decided to keep only 10 columns in the building. So those columns were selected by the designer of the building as the most critical elements of the structure. So the Punggol buildings consists of, the Punggol complex consists of 6 blocks founded on piles. And here you can see the building which is in progress, in construction. So every building has 19 stories and 6 units per story. And columns, in case of Punggol, were cast on site. But for some other project, the columns were also produced in the plant, in the prefabrication plant. So here now we can see the floor level of the building, and selected columns are presented now here. So there is 10 of them in total, and so there is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you can see that there is a kind of asymmetry in the equipment. So you see that most of the sensors are installed on, let's say, left side of this drawing, and much less sensors on the right side. And this is because in this area here, you can see there is multi-story void. That means that first 6 stories of the building were not real stories. It is just empty space because orientation of the building is made in that manner that in this area there is a parking, and so there is no place for the stories, for the apartments. Sorry. Few photos of the installation. So as I mentioned, here we have the cast-on-site columns. So the sensors were installed practically in the rebars, in the rebar cages. You can see the SOFO sensor. Let me just... So here you can see the SOFO sensor, which is installed here on the rebar. Then you have the passive zone that is going around, entering in the junction box. And then the junction box was protected since it was also embedded inside the concrete. As I mentioned before, we have also some sensors that are embedded in the prefabricating plant. So the manner of installation is practically the same as you can see on the left side photo. It is just only that the sensors were installed. You can see here the sensor. The sensors were attached to the rebars in the plant, and then after the concrete pouring, they were transported to the site. So practically after the pouring, you could see only the junction box with a small window for the connector. And when the measurement was to be taken, this window could be open and connector from the SOFO reading unit could be plugged in. And like this, we could perform the measurements that were actually manual measurements. So on this project, it was decided in order to reduce the cost to perform the measurements manually. So the campaigns of the measurements were performed with some regular intervals, but not continuously. So every time someone had to go on site to open this small window and then to plug the connector and to perform the measurement. Okay, so in the last photo you can see actually the connector coming from the extension cable from the SOFO, which is plugged inside the junction box. In the next slide, you will see how the completed buildings look like. So obviously when the buildings are done, they look nice. You can see the blocks of the Punggol. And you will also be able to see the operator of SMARTEC's distributor in Singapore, SOFOTEC, performing the measurement on one of the buildings. So you can see here the buildings are very nice and with nice design, very modern buildings, 19 stories tall. And here on the right photo, you can see the operator of SOFOTEC, which plugged here the sensor inside the box, and he is performing the measurements manually. So next slide will show actually the 7 years results. And this is very interesting slide showing different stages of the building life. So that's what we actually expect to see in this diagram that now appears on your screens, is during the construction stage we have compression in all the sensors, and that's what is also very good to see is that most of the sensor measure practically the same value or nearly the same value, which indicates that all the building is progressing in a good manner. That means all the columns are deformed in the same manner. So every new story added, one measurement was performed, and this measurement indicates that all the columns settled, deform, compress for the same value. Except one column, which is column C9, and if you remember, I mentioned it in the beginning of the conversation, this void area in which the sensors are less loaded because there is less stories with apartments. So then we can see once the construction is finished, practically the most of the load is inserted in the columns, and that what we see that is evolving in time is actually mostly rheological effects like creep and shrinkage. So we can see that all the columns continue to deform, but now somehow their values start to be more scattered. So they start to if here at the construction stage they were very close to each other, now they start to be very far from each other. We performed several 48-hour campaigns. That means we measured over 48 hours continuously, every hour, in order to see what happens during one day, what is the daily fluctuation in one column. As you probably know, in Singapore the temperature is very stable over a year, so we have the variations of, let's say, plus minus 5 degrees around, so 27 plus minus 5. So this is why we didn't expect big jumps like you could see, for example, in the slide that Luca showed in his presentation of Minneapolis. So here everything is much more flat. But however, those daily fluctuations can influence the analysis of the data, since in this project the temperature was not monitored. So here you can see one 48-hour session, then another one, then the third one, and fourth one. And here you can see in between two 48-hour measurement sessions, there was a tremor that happened due to the earthquake in neighboring Indonesia, and we were able to catch this event and to make the post-tremor evaluation of the building. So people in the building actually could feel the movement of the building. They called the authorities and asked for the opinion, and then we were able, based on the measurements that we performed, to give the answers about the health condition of the building. So at the local level, first we made the data analysis based on the fact that sensors measure axial deformation in the columns. So we were able to determine the measured strain in the column, and then we could evaluate whether the strain is acceptable by comparison between measured strain and estimated value from design. Then we were able also to compare between the measured strain and ultimate values that are expected. And we also could use 48-hour campaigns in order to learn the building behavior caused by daily temperature changes and inhabitant fluctuations, and also to record the health state of the building now when the building is in good condition, and to use this as a basis for the future. So average strain measurement by sensor, if I use the simplified formula, can be expressed by total strain that is actually measured by sensor is equal strain due to the load, or elastic strain in case we are not in the plastic zone, plus creep, plus thermal strain, and plus shrinkage. So it's a kind of simplified formula that applies very well for the concrete. And in our case, so we have thermal strain, total shrinkage, creep, and elastic strain, or strain due to the load. So in our case, the first one, the thermal strain was neglected because, as I mentioned, temperature in Singapore was more or less constant, so it was not measured. Then the total shrinkage was estimated using the CEB FIP model code. Creep the same, so using the same model code, we estimated the creep. And finally, we used design values for the elastic strain, and then practically we were able to reconstruct what is expected, what is designed, and to measure with that what is obtained from the sensors. So in the next slide, I will show two comparisons for two columns, for the column C3 and column C9. I will show approximate lines for the first 4 years of the monitoring. So here you can see, for example, for the column C3, the first line on the top is estimation of the shrinkage, then estimation of the creep, then the estimation of the elastic strain based on the design, and here you can see the line with the romps, that is the estimation, theoretical estimation of the strain, total strain evolution, and the measurement of the sensor is presented with the dashed line. So you can see that for this particular column, in the first stage, we had very good agreement between the numerical model and the measurement with the sensor. But not to show, let's say, the best example, let's see another example. Let's see the column C9, that we say that measured less deformation from expected. In this case here, we could clearly see that this column measured less than expected, and that probably this column is either over-designed, either underloaded, and actually the explanation for this was found in the fact that there is, first of all, the void area around this column, and then the second, this column is very close to the core, so it is also possible that the core of the building is attracting more, since it is much stiffer, is attracting more loads to itself. So next slide is showing comparison between designed and measured. This time the comparison is just to show the differences between the different approaches, between different numerical models, and that's what is measured. So I hope the slide will be uploaded soon. So here on this slide, you can see in the red line, you can see the measurement performed by SOFO, and all the other lines show you some theoretical predictions that are based on different models like parabolic serviceability load state, linear serviceability load state, parabolic ultimate load state, and linear ultimate load state. So we can see that depending also on the numerical model that we use for the comparison, we can get different results. In this case here, we can see that this column that is selected was out of 3 of those limits, but it is still within the 4th of the limits between linear ultimate load state. Just to show the next slide, which is 48 hours measurement in 2004. In this slide, we'll be able to see the fluctuation over 2 days in strain and in temperature. So here you can see with the ROMs, you can see the fluctuation of the strain over 48 hours. And here you can see the fluctuation of the temperature. So you can see the temperature is really, temperature fluctuation is really very, very small. And also the deformation is really small. We speak about some less than 20 microstrain all in all. Another 48 hours example is just comparison from year to year within one sensor. So it is interesting to see what were the daily fluctuation in year 2004, 2005, 2006, and 2007 performed on the same sensor. So now you can see here the line. So in 2004, we have some daily fluctuation in the blue line. Then the year after, we have practically similar result, but complete line is shifted down, and it is shifted down because of the creep and shrinkage. And then the same happens the year after, but the fourth year we have nearly the same measurements as during the third year. So in this case here we can say that the creep and shrinkage are more or less stabilized and they don't evolve anymore in a significant manner. So I will just jump to the slide which is showing also some environmental behavior around the building. So you can see the relative humidity and you can see the average ambient temperature with this is the average value, for example, and this is maximum and minimum. So you can see that average humidity is nearly the same all 4 years that we did the monitoring, and the temperature is also more or less within the same limit. So it's about 27.5 degrees plus minus 0.5 degrees average value. So we have pretty constant conditions around the building. Then it was very interesting to see evolution for every single column, and here we can see we can already see some anomalies in the behavior. For example, if you look the column C3, which is presented here, we can see that from year to year the value of the strain in this column is actually increasing in terms of the absolute value of the strain. So we see that actually this column is decompressing, while some other columns are much more compressing, like column C1 and maybe column C2. Some of the columns are pretty stabilized, for example, column C4. Some of them, they have big fluctuations depending on temperature, like C6. So you can practically see for each column what is the behavior. So now we'll focus more on this column C3 that actually has the, let's say, negative behavior. We expect the strain to increase in time due to the creep and shrinkage, but the strain in this column is actually decreasing. But before we go there, I will just quickly show you the post-tremor analysis that we performed. As I mentioned, in the neighboring Indonesia, there was a strong earthquake that was felt like tremor in Singapore, and we had one measurement performed before the tremor and one performed just after the tremor. So we could see that there were small changes that are detected by the sensors between before and after, but those changes actually, if you compare with the fluctuation, daily fluctuation in year 2005 and in year 2004, we can clearly see that those small changes are actually within the limits, and that we can practically make conclusion that there is no damage or no any influence of the tremor to the behavior of the buildings. So now we are going to make an assessment on the global level. So I will go back to this column C3 that was, let's say, problematic. So that what we do is comparison of strain developments in columns per each unit, comparison of differential deformation of columns, and linear correlation between the sensors. So before, we have already mentioned that the column C9 measured less strain than the other columns. And if you make a zoom just during the construction phase here, we can clearly see that this column measure actually strain which is proportional to the other columns, but by absolute value it is much smaller. So it was judged that the column is overdimensioned for the area where it is, and it helps improving design of the structure. Then if you perform the linear correlation in long term between the neighboring sensors, for example, here we can look the unit B, which consists of sensors C4, C5, and C6. We put on the x-axis the sensor C4, and on the y-axis we can put the other sensors. Then you can clearly see that there is a linear correlation between the sensors, and this is actually what is expected to happen in a building. So if you have the vertical, let's say, compression in the columns, then you expect all the columns to act in linear dependence to each other. But in some cases, this is not fulfilled. In some cases, we don't have really linear dependence. And this is the case of the unit A. Now you will soon see on your screen the diagram of linear correlation for the unit A. In this unit, actually, it is very obvious that there is no linearity between the behavior of the columns. And I'm just waiting that all of you can see this diagram. I'm sorry, but it seems that the network is a little bit slow now. Okay, now you can see it. So here, obviously, there is no linearity between the column C2 and the two other columns C1 and C3. So you can, in this area, you can see that we detected some event, so something happened there. That what actually happened there, and that's what you expect that happened there, is settlement of the column C3. Because now, if you plot the diagram showing only these three sensors in long term, you can see that C1 measures something which is bigger than expected. If you see this line, how it is going down, it is really much down. And C3 measures something which is smaller than expected, because up to here, it was developing well, and then suddenly it became pretty constant. And then from this point and on, we even see a kind of tension appearing in this column. So we did some very, very approximative analysis using some very simple numerical models in order to try to estimate how big is the settlement in this column that provoke this change in the diagrams. Here you can see those models that we used. And actually we could see that was settlement of the column C3 was evaluated to be approximately from 0.25 to 1 millimeter. So that means that this event is not really dangerous for the structure, but it shows how sensible is the monitoring system since it was able immediately to detect this type of the behavior of anomalic behavior. So now we will see some other interesting thing that we get out from monitoring. Since the Punggol blocks were composed of different buildings, then we compared, for example, two buildings in order to see the behavior, and we could see that in two buildings that are built on the same site with the same constructor, with the same type of the concrete, the sensor measure approximately the same value. So you could also use the system as a quality control of the construction of your building. So it was repeated not only for this block 160, but also for the block 166. Here you can also see that comparison between two blocks shown that we have practically with the same contractor, with the same quality of the concrete and the same design, we had very, very similar results. So I hope the slide will update soon and you will be able to see this. Okay, so here you can see one building, you can see the other building, and if you look the values here, it is between, let's say, 500 and 800, and here is the same between 500 and 800. So we can say that we have very similar results. Okay, so as a conclusions, we can say that detected overdimensioning of the column C9 will help designers to improve modeling. We can say that we detected the differential settlements in the columns with very small magnitude, so it doesn't really influence the performance of the building. But settlement is, however, not stabilized yet, and the monitoring should continue in long term. The 48-hour sessions confirmed sound performance of the building in long term and made possible the post-tremor analysis. The creep and shrinkage stabilizes slowly, and now they are developed approximately of 85%. And from now on, the dominant influence starts to be the ambient temperature. So the Pioneer Monitoring Project for Singapore high-rise building was presented with more than 7 years of long-term monitoring. We had very successful monitoring, and we were able to register important stages in structure life. We enlarged the knowledge concerning the real column behavior during the construction, including the rheological effects. And in spite of limitations such as not monitored temperature or no continuous readings, results lead to important insights of actual structural behavior. Monitoring strategy developed and successfully applied. Monitoring system SOFO was properly selected and fully responded to design criteria. I must mention that here we have, for example, 10 sensors installed in the building, and after more than 7 years, we still have all of them functioning properly. So the use of fiber optic sensors on such a large scale set directions that will help designers better understand the behavior of tall buildings during its life cycle from construction to the service conditions. And this project is presented in details and used as an example in our book, Fiber Optic Methods for Structural Health Monitoring, that is available at SMARTEC. So now I'm ready to answer some questions that you asked. So the question that I have is that in a project where we cannot afford to install sensors on all columns and install only to chosen columns, is it advisable to prioritize installing sensor to certain columns, such as the 4 corner columns and so on? So here the answer is that the best way to choose the columns in which to install the sensor is based on the design. So it will be important to see what columns are, let's say, strategic, so what columns are the most important, what columns are the most loaded, and to choose those columns to be equipped with the sensors. So sometimes, you know, when we speak about reinforced concrete, the performance of the reinforced concrete depends on the dimensions of the columns, but also on the quantity of the rebars that you have inside the columns. So it is very important. If you don't have, let's say, the design available, then we can try to install we can try to find out by engineering experience what columns can be the most critical ones. But still, the best manner to choose the columns to be equipped with the sensor is to make your decision based on the design. Okay, I didn't have any other question for the moment, so I think we can finish this presentation. Okay, so I would like at the end to acknowledge the SOFOTEC Singapore, who is our SMARTEC distributor in Singapore, and of course hosting and development board, who shown really very good collaboration and very big interest in the fiber optic technology and supported us very much. Okay. So I would kindly ask you to answer to questions that you will receive at the end, and they are regarding evaluation of this type of the seminars, and your answers will really help us to improve and to make those presentations better. So this is our second presentation, and we hope that every next presentation will be better than the previous one. Okay, thank you very much.